Thanks, Christoph, and thanks to the organizers for the invitation to give a talk about these three topics here. My name is Martin Rittner. I come from a global Bosch company. Hopefully my colleagues who gave presentations the last 2 days introduced already our company. Me personally, I'm a senior expert at a corporate research entity for assembly and interconnection technologies for power electronics with a very special focus for the power module technologies. So far, it fits quite well to the demands of the 3 days event of the South School of Transform and YESvGaN public funded projects. Well, the basic problem to me was within these 1.5 hours to cover all of these 3 issues and tasks because each of them could fulfill a 2 days workshop or presentation events or something like that. But nevertheless, I try to give real good insights and, let me say, demands and current knowledge, current basics to them. Well, but nevertheless, the main focus will be on the packaging issue because it's quite important to everybody of us. Quite typically, it seems to be quite far away if you are highly involved in the chip issues and chip architectures, chip process technology, but nonetheless, at the end of the day, you need to package your dies, your bare dies then, to integrate them in a, let me say, pure or real hardware unit for the later functionality and the later application then. So far, it's no surprise that this will be the main focus. Packaging technologies, I want to introduce them to you to give you a certain feelings and experience about the latest trends here and demands and requirements. These technology in principle are highly coupled with this reliability assessment. First insight was given already by Rittner today's morning, but I will extend the insights here, and the same is here for the standardization activities. Already some information was given by Tobias, but I will complement them with additional information and further insights. With a very special focus on mind setting and methodologies here. But let's start now with this issue of industrialization. Lots of you, a lot of these persons in this room are highly involved in new innovative tasks, ideas, or for let me say, new functionalities in chip, new generation of chips. But at the end of the day, you have to sell your product. This is at the end of the day the main task for the people in industries then. And therefore, let's have a look in this industrialization issue. Just one slide to cover the entire supply chain from, let me say, base material. This is the ingot of a semiconductor cell in Bristol to the later application. Well, okay, it's highly compressed for sure, but nevertheless, it gives you a certain feeling about time scale and a little bit a feeling of the money you need. And let's look at the daily messages in the public domain regarding Intel invest in Germany and regarding TSMC invest in Germany. This is really important here. Yes, you see new buildings, factory, you need a presuming time of 4 years, you need an invest of around about 20 billion euros or dollars or something like that. Quite important, impressive numbers here. And you have this, you have to keep this in mind when you want to perform semiconductor industries. And here is the time scale. Yes, product development, chip design. You have this time consuming 1 up to 3 years. You have this running time from the single crystal to the application. It's shown here. Back end is very important. This is the main task then with the look at technology in the second part then of my presentation. And then you come to semiconductor chip as packaged one, you go to the hardware, the system, and then at the end of the day you have some industry branches, but I don't know any industry branch which could work without any kind of electronics nowadays. So therefore it's just a few examples showing the needs and demands here. Please keep this in mind because this time-consuming process you have to consider in any kind of your product development. If you decide for a certain product, a certain functionality of a chip, yes, you have to think about this time-consuming process here till you want to go into product then at the end of the day. A very special look on the process landscape in a fab here, just to show the complexity and the, let me say, the basic why you need so long time, this time-consuming processing here. This complexity, just a few examples here, you go from the first bare wafer to the next steps of architecture, processing your architecture inside of the wafer, and then we have this here, this let me say dice structure on the wafer. This complexity is for people which are outside the semiconductor industry is quite hard to understand. Why is this time-consuming process running? But it is, and therefore, with these decisions for supporting semiconductor industries or politics, it's quite important to show up here. Look on this time scale when you try to support semiconductor industry from politics side. This slide shall show up that semiconductor industry and as well electronics industry is a real global industry. We have a global supply chain. Just for some highlights in the, let me say, this overall process, the growing semiconductor step, the step of processing the wafer, electrical function testing. Very important is the assembly one, then the purchase of the assembly. It's not just a question of sourcing your semiconductor part and component globally. It's a question of this process, this shown process on the first slide. This process as well is already a global process, not just a local one. And with the very special look of Bosch or the automotive industry, which is a real good example for the application of lots of electronics function and therefore a lot of semiconductor needs inside of a modern car, this slide shall show up the width of needs of a special type of semiconductor. So today we have a special focus on wide bandgap power semiconductors. Okay, this is a real very close look on all power electronics applications inside the electric vehicle, for modern electric vehicles, but nevertheless, this slide shall show up. We are talking about a lot of applications and a lot of special parts and semiconductor functionalities, very special with the look of the, let me say, the support demands for innovative research on semiconductors. The line widthnesses here, even as the numbers on each, let me say, special branch of semiconductor demand shall show up. We will cover all of them. So we have examples and applications with the, let me say, front end, absolutely front edge of technology and line widthness, space widthness, but as well we use, let's say, state-of-the-art widthness. It's very special for the power semiconductors because we have to block such high voltage numbers around about 1 kV at the end of the day, and therefore we have this large spreading. So nearly all kind of semiconductor technology is found in a modern car nowadays. Okay, let's go into the depth of technology. This means packaging technology. First of all, I have some slides with me about the definition you need to keep in mind when you talk and discuss with experts, because looking on the domains you have to involve for the later application, it depends a little bit from which domain the counterpart of your communication is from. Because just here from this example, you could talk about the aggregate or system level, you can talk about the electronics assembly level, you can talk about, for example, the power module level, or in comparison to that, maybe the discrete packaging level for a power semiconductor. Just for one example here, if you talk with experts from tier 1 or tier 2 suppliers and you talk about something about a component, you mean the electronic components. It could be a discrete one, some of the black discrete packaged ones, or a passive component one or something like that. If you talk with an OEM experts, then a component is typically the application level, so the aggregate here, like this example is a drive inverter unit with a DC-DC converter inside from Bosch, a very early generation here. Then they talk about a component, but as expert for assembly and interconnection technology, a component is often or mostly the discrete component or the module or something like that. Furthermore, with a look on the electronics packaging world, you have to discuss on which level of hardware integration or level of build-up you want to discuss, or you want to find innovation or something like that. On the left side is shown the world of so-called first level packaging. First level packaging with reference to the bare die. This means the packaging of the absolutely closed surrounding of your bare die. Here in the cross section, it's quite shown. The example is here from our EPS system with a low voltage blocking silicon power semiconductor here. You see here the die itself is a silicon part, then the bond foot here, the die attach, it's a soldered one, then you have here the substrate, and then the substrate interconnection to something like a base plate or heat sink. So first level packaging means the direct surrounding of your bare die, independently of what kind of packaging you want to implement or integrate it. Then you have the second level packaging, and this means typically the PCB level. PCB level means you have a quite diverse selection of components, active and passive components here, with several types of packages, and the process technology as well differs and are quite diverse. So that means you can apply SMD reflow soldering or adhesive technology, THD technology, and such things. I will give a short insight with a further slide then afterwards. So this is the world of, let me say, your hardware integration level. Yes, second level packaging. And it's quite important that you can differ between these both worlds. Okay, looking on our multi-chip power module as well, you have to differ into two basic worlds or two base technologies, you can say. First of all, we can talk about a so-called open construction module, which is quite conventional looking on the early times of electrification cars, because this was the baseline for industrial world. Industrial packaged power modules in, let me say, around about 20 years ago, typically has seen this package type, the so-called open construction module. It's a polymer frame here. We have this half-bridge assembly of power modules, glued or adhesed on a base plate, and then you have a polymer package, a polymer cover plate, and inside there's some soft silicon shield inside to fill up all of the free space and open space with solid material there. Then let me say the more or less modern version of multi-chip power modules is this molded type. But molded type is quite similar to a discrete because it's the same, let me say, packaging technology for a single chip discrete part. But nevertheless, here you see a real huge part in comparison to a discrete component, because you have here around about, let me say, 12 chips inside, just a single chip from a discrete package here. So it was a huge challenge to transfer technology from discrete world to such a molded power module here. And what we have seen in the past is a real agile and dynamic development in the diversity of technology possibilities. This old world of industrialized products from open construction was quite conventional in terms of you have a PVC, so-called PVC substrate, yes, ceramics, DCB. Then you have the die attach technology, it was soldered. You have the chip itself, okay, for industrial application it was the IGBT or the freewheeling diode chip. Yes, then you have your aluminum bonding wire technology on the top, and then you are ready with your product. With the demands for automotive industries in terms of robustness, reliability, and in terms of cost effectiveness of your product, you have seen you see now a quite diversified world of technology possibilities. So we see high performance ceramics, we see lead frame solutions, we see besides the soldering technology, sintering technology, we can change from aluminum bonding to more robust copper bonding solutions, and so on and so on. So in sum, you see a real, let me say, a zoo of technology variants you can implement in modern power modules. Either it is, let me say, conventional silicon world, or it could be a wide bandgap world like silicon carbide, or for sure the gallium nitride world here. So these are the domains you have to fulfill to build up your power module. Then, with my presentation, I don't want to go in the latest depth for all of them. I just framed them in red, which I want to highlight with the next slides. And the dashed one, they are as well involved with my presentation. Those slides then here. Okay. You want to discuss a second interconnection technology, you have to think about the, let me say, the real world, the physics of your material. And quite important, and then one of my main messages here is don't underestimate the inherent characteristics of the materials that are involved in your packaging, because it's an endurance situation. You cannot cut off some characteristics of a copper material, because copper has a combined situation, or other materials have a combined situation of their functionality. Functionality in terms of mechanical, you can discuss about the Young's modulus, shear modulus, plastic deformation, so on and so on. You have to discuss and consider thermal situation, yes? So the specific conductivity or the absolute resistance, the specific capacity and so on. And for sure, electrical functionality in terms of it should be insulator or not, it should be metal, conductor as metal, or it should be a semiconductor or something like that. And all of these characteristics are inherent given, yes, and you have to consider all of them in the same time. For one example, I want to highlight solder material characteristics with these examples of cross-section here to give you the feeling about, let me say, the complexity you have to discuss if you want to design and you want to select a proper packaging or the technologies for your packaging. You have to think about metallurgical situation. It could be something like an alloy. It's very typical for solder material. Just regarding the base situation of the base alloys is quite complex, but furthermore, you have to consider microstructural issues like morphology, grain coarsening, looking on the later loads, sliding of grain boundaries and such things. Then the physical properties in principle, okay, this was the slide before. Then you have to consider fatigue mechanisms, because you will damage or you will age, this is the first step, you will age your material under the loads of your later application. And therefore you have to think about which is the material behavior, the material characteristics later on under a certain loading in your application then. So please keep in mind, material systems, or for this slide very special, the solder material systems are quite complex systems. So material science is really an exciting science and really important as well for electronics industry. So electronics engineers should have, let me say, a broader thinking and broader mind setting than just designing a circuitry. This is the main message here. Okay, let's have a look on mechanical issues of materials, basics on the so-called stress-strain relationships. This is a very famous curve. This is the Hooke's law. I would say everybody in this room know about this, but nevertheless, it's you need a higher complexity for your design, because you have this border of elastic region and plastic region here. And overall, we have this quite complex curve, which are the tipping points between elastic plastic, which are the tipping point to overloading or overstress, or even to the entire fracture of your material system then. And you have to analyze nearly to all of your very special metal or alloying systems. You have to need the knowledge about such behaviors to implement it in your later design for very special thermomechanical design considerations and such things. Regarding soldering, regarding the base alloy, you need thermodynamic knowledge. This means here quite typically you want to use eutectic solder systems. This is the eutectic point. This is the principal scheme for a binary system. This point is, for example, quite important for how the process temperature what you want to apply. This is correlated to your equipment. This is as well correlated, which I will show in a later slide. This is as well correlated to your reliability. So the knowledge about your thermodynamic situation of your solder alloy is quite important for your decision or selection, which one you want to have in your application later on. So here, soldering, what does it mean? Process. On the one side, you have this so-called reflow soldering. And this, on the left side here, you see the typical temperature profile you will have to apply to perform the process technology of soldering. So you have a solder paste deposit on the circuit carrier, applied by screen or stencil printing. Then you have the placement of your electronic component. It could be a discrete, it could be a passive component. The assembly is subjected to a control heat in the furnace system. Then the solder paste reflows. This is the name given here. The solder paste as a solid material then reflows into a molten state during this temperature ramping process, creating later on the permanent solder joint then. And this is the preferred process technology for second level packaging as shown in the slide before. As well, it is a state-of-the-art die attach technology for first level packaging. Yes, principally, this is the same, let me say, process technology for the conventional die attach as the high lead containing one you will find nowadays as well as a standard metallurgy solution for your die attach in a discrete package. On the second hand, you can discuss about wave soldering. This is given in the picture here on the left side below. This is a bulk soldering process, so this is a solder bath in the liquid state. This uses a pan of molten solder with a pump, and you have then a upwelling situation of solder liquid then. And the solder wood passes on this wave then, very special from the backside. Then you get this wetting with solder material on your pins or something like that, which looks on the backside of the PCB. And then you get a good contact to the wave, and then the assembly is done with this process shifting the wood from the left to the right side, and then the solder happens. You have a solder joint then on the back side or even through the rear through your PCB then. And this process technology is quite typically for second level packaging. Looking on the material selection, we know about a lot of solder materials and alloys. But the question is then, okay, which one we should use? For second level packaging, quite typically is this selection here. Not all of them are used nowadays in electronics because they have advantages, they have disadvantages for the specific alloy. The old world was this tin lead with this eutectic formulation here, 183 degrees C for the eutectic one. But regarding on these all things of regulations, ROS, W, EEE and ELB from the EU legislation, this is banned principally, okay, for some disciplines you can apply this solder alloy as well. You can apply tin zinc, for example, but okay, you have then maybe some problems with corrosion issues and such things. Then you have these lead-free base solutions. All of them you can use for your second level packaging. Okay, this is a little bit higher value, this antimony alloy here. So I would say this here is quite conventional now for the second level packaging. Is the most used here with this lower temperature here of about 270 degrees C. For the first level packaging, you have to discuss this world with higher melting temperatures. So this lead containing here is quite conventional for the first level packaging nowadays. But the problem is, okay, a lot of people want to get rid of them due to these regulation issues. Why do we have to differ in this range of temperatures? This curve is quite important for, let me say, the base selection you want to perform with your design and your process technology. The relationship is this homologous temperature. Because the usage temperature, or in kelvins, and the melting temperature, the quota here is the so-called homologous temperature. And there's a very famous curve here, which covers nearly all metals and metal alloys here. And you have this state of strength in a solid or solid liquid, or okay, here all materials are then liquid regarding the homologous temperature. So one means you have this phase change from solid to liquid here. Why is this important? Because this numbers you could refer to the demands of soldering regarding to the application, the load from the application temperature. So this value of 10.4 at room temperature, reference to room temperature means 450 degrees C, and this is the border between soldering and brazing world, because you can think as well about brazing, but okay, then you need real high melting alloys. And looking on this standard alloy here, tin lead, at room temperature C, it's already 10.65 here. And this is a really huge value regarding on the application. So it would mean in comparison to stainless steel or something like that, that you have to apply a load roundabout of 600 or 700 degrees C. So this homologous temperature shows, let me say, an indicator as loading on your metal or your metal alloy then. It's quite impressive in comparison to steel then. Yeah. Looking on alternatives for lead containing solder alloys, because everybody wants to get rid of them. For second-level packaging, we have now this lead-free solution here. It's preferred substitute for this eutectic tin lead. It's a robust process. It's quite conventional nowadays. 20 years ago, there was a lot of, let me say, technology struggle and research in tasks how to implement this alloy for the industrialization. It's very special for the second-level packaging. For first-level packaging, you can think about this bismuth alloy. You can think about a gold-containing alloy. Okay, the upper one is the standard for first-level packaging. Substitutes, okay, unfortunately they have a lot of disadvantages. So this is high costly. This is okay. This could be a low-cost alternative, but it's high brittleness. So if you see this curve, this operating temperature and the solder melting temperature, so this is a little bit a different sketch regarding the homologous temperature here. Yes, you see, okay, you can find alternatives to this high lead containing situation, but at the end of the day, it's quite hard to substitute it with another solder now. Okay, then the question is, okay, soldering, quite hard to substitute the lead containing one. What about brazing? Okay, brazing, it's quite, and it needs a large temperature. So the lowest melting brazing alloy is this one at 577 degrees C, and it's aluminium silicon 12. So we have something like an alloy gap. This is the official border regarding the homologous temperature. Lower temperatures are related to soldering material, higher temperatures are related to brazing temperatures. But here's something like alloy gap. Here we have no material solution, it's not existing. The periodic system is limited here. Regarding a high melting situation, this zinc aluminum alloy, okay, it could be something like a substitute for high lead containing solders, but then you have a lot of issues with corrosion here. Yes, aluminum and zinc, it's so hard to control it under corrosion loads afterwards. Are there alternative technologies available? Yes, there are. You can think about sintering of metals. And this is quite conventional here, the so-called transient liquid phase diffusion soldering. You need a high melting material, a high melting metal like nickel in this example, and a low melting metal, this is the tin. And then with temperature, pressure, and a certain time of your process run, then you have a diffuse layer between your joining partners A and B. Then at the end of the day, you talk about this TLP layer. It's around about several micrometer thickness, and it's a real good solution for just little parts like sensors, or it could be as well an LED, it could be as well a power semiconductor, but you need just small areas. Then it could work. Then you can use in a quite similar way so-called reactive foils. They work quite similar, but the buildup is in the nanometer scale here. So given here the example with nickel and aluminum, you can as well apply a little bit of temperature. You need activation energy. It could be temperature, it could be another source here. As well, you need pressure and a little bit of time, and at the end of the day as well, diffusion soldered material you get as let me say the attaching system between joining partner A and B. So here, in comparison to each other, for this more or less classical way, you can use a lot of a variety of high melting metals given here and shown here, as well for the low melting systems. You find such solutions in well-established die-attach systems for optoelectronic devices, for example, and such things. And I would say Infineon has a solution for low-voltage silicon MOSFETs as well. This high-temperature capability and high-loading situation on such a joint is given to the primary IMC microstructure then. So important technology questions are always the reliability and robustness of such a defined and generated joint then. Looking at the reactive foils, they are commercially available. Just for one example, Indian Corporation performs with these nanofoils, so-called nanofoils. They have, in this interface, they have characteristics like solder-like or braze-like, but nevertheless they are quite costly, even nowadays. So I would say this is no proper solution for power semiconductor packaging, but okay, you can think about it and you can try it. Further research activities are ongoing to go down with the cost situation here, but this is covered, or this is just possible with the raise of the layers to a more or less sub-micrometer scale, go away from the nanometer scale then. But then the question is, how is the process, then how will the process situation then act the same? Is the diffusion process the same? Is the quality of the characteristic of your joint the same, and so on? You have to characterize and analyze them in any way. More or less well established now for power electronic modules is the so-called sintering technology, silver sintering technology, or some people call it low temperature joining technology, in short LTGT here. So the build-up of your system is quite the same as shown already in the last slide. You need the joining partner A and B. You have this very special metallization situation. But then, in a way of classical silver sintering, we have a paste situation with the silver flakes inside. As well, you need here time, temperature and pressure. And then you will receive this silver sintered layer. An alternative is a nanoparticle process. You can apply. Then we have the parts on a sub-micrometer scale or even a nanometer scale. They are more or less spherical, and not so far the flake type then. Okay, the process situation from the parameters is a little bit reduced, or is reduced on the pressure scale, so it's below the megapascal scenario. But you need a little bit more time, and as well you get something like a silver sintered layer then between your semiconductor part and your circuit carrier, as one example you can join. To compare each other, this classical process, this silver sintered classical process, you can apply paste on a commercially available situation. A lot of them provide here a suitable paste. The functionality is surface, you need a functionalized surface. So nodal surfaces are highly welcome for this process landscape. So copper blank you could apply as well, but it's a little bit critical. You have to be sure that no oxides or no further residuals on the surface. Then it could work, but it's a little bit more critical to these alternatives of nodal surfaces. For the characteristics of such joints, you will receive a dense and low porous joint with good connection to the joint partner surfaces, so we will reach something like a maximum reliability in this classical way. It's already industrialized for single-sided power modules, but nevertheless we have some open technology questions and even research tasks for this process part here. So the process transfer to double-sided systems. If you want something like a sandwich type module with a counter substrate on the top side of your power device or something like that, then it's quite hard to apply this process technology doubled on both sides of the semiconductor, and I don't know if you will really see something like that. Well, Semicon applies this, but they use a flexible substrate on the top side, so it's quite hard to say it's a real sandwich. Okay, it principally is, but with this flexibility of a flex foil, you can discuss about a real sandwich or something like that. So, and the integration of further components in power modules is quite hard with the silver sintering process because you have to apply this pressure. Soldering works without pressure, so it's so highly flexible, and for sure this is the reason for this state-of-the-art nowadays as well, because you can integrate a lot of further components on your power module there, like an NTC thermocouple sensor or something like that. For sintering it's quite hard to apply as well, and then we can have to discuss a double-step process. First of all, sintering for the power device, and then the second one is for the other components there. Let's have to look at the nanoparticle process. As well, pastes are commercially available. As well, you have to discuss the functionality of the surfaces. The characteristics of the joint is quite porous then, with reduced connections to the joint partners as well. Then you have the reduced reliability. LED applications, they perform with them because they have just little parts as a semiconductor to join on your substrate. And you have not this, let me say, power cycling condition as a load for the joint in comparison to the power modules, and it will work really properly, and it's let me say, more or less state of the art here, but it's for power modules, there's still some open questions here. So the process transfer to maybe molded power modules without any losses in reliability, and maybe the question or the solution for an easy integration of further components would be possible here then. Okay, let's have the situation. I put the transform icon here because me personally, I'm highly involved in the transform project, but nevertheless, all of the given information are valid for gallium nitride based devices as well. In the transform project, I can say hello. Here we are. We want to apply copper paste instead of silver paste then. The principle is quite similar. This means you need temperature, pressure, time, but additionally you need a controlled process atmosphere, for example nitrogen here, but at the end of the day you will receive as well a copper cinder layer between the semiconductor die and your circuit carrier. So the potentials here, in comparison to silver sintering, cost savings, okay, the raw material prices for copper are lower than for silver, but nevertheless you want to apply something like a paste, and at the end of the paste could be nearly the same price, conductors nearly the same price than in comparison to the silver paste here. I would say the most important issue is the chance and the potential for the reliability increase. So the coefficient here is more capable in regarding to the semiconductor world. We have a higher yield strength of copper in comparison to silver. We have then an homogeneous material situation, very special problem coming from the substrate side, an ECD or AMD substrate. They want to, or you need extra costs for this plating, for this noble plating on the surfaces. So considerable potential for reliability increases to be expected, and there was a research task within Transform project. Right. Let's have a look on the top side of the chip, not so far the die attach or the back side. Let's have a look at the top side. Well, principally, you can talk about the sandwich type module. Then you can have the same discussion like shown in the slides before, because you can double then all considerations from the die attach to the top side then. But quite conventional as well nowadays is bonding. Ultrasonic wire bonding for the chip topside technology. Just giving the example here how it could work. You have this ridge tool, you have this lead for the wire or for the ribbon, and then you have the cutter to separate then the already bonded parts from the power module then. And the process parameters are given here. Usually something like a static force to push it down, the wire or the ribbon, and then you apply ultrasonic power, and then you will have on a real short time scale something like a welding process. Even all experts in the world are discussing, is it really welded or is it something alternative to that? But it's a real solid state and well-connected situation between the wire as auxiliary material and the top side of your semiconductor then. Principally, you can discuss two worlds with this ultrasonic bonding technology. One is more related to the logic world. This is the so-called ball wedge technology. It's more or less related to the thin wire bonding. You see here the ball and then the loop to the heel over there. Typically, this is on the semiconductor surface here, and it's more or less ASIC or highly integrated logic parts here you want, because you have here the flexibility to go in the azimuthal angle to all directions to the surrounding of the die then. For the power world, more or less, typically is the so-called wedge-wedge bonding. It could be applied to thick and thin wire bonding, as well to ribbon bonding, and we have then you see here two wheels, one on the power semiconductor then, the second one then on the substrate. So, just to differ, let me say the quite conventional state-of-the-art world on the left side, this means standard aluminium bonding to the right side, and the right side is as well related to the Transform project. Standard aluminium bonding means you have well-established processes as heavy wires or ribbon bonds. You can use the traditional chip metallizations, okay, they are adjusted to each other. This means ALSI, ALCU, ALSICU, and they are typically designed for this process landscape. But the limitations are the electrical connectivity, the thermal connectivity of aluminium, and the power cycle robustness. Some aspects are already given in the morning. The advantages or the differences with the look on copper bonding here is you can apply as well to heavy wire and ribbon bonds. You need a new chip metallization because this one here, these metallizations, they are too soft. They are really too soft to cover and to protect your underlying active structures in a power semiconductor, very special the gate oxide. This means you need a change from the standard metallization, very referred to a copper metallization. It will work with around about 30 micrometer on the top. Okay, it's a real new world then in comparison to this traditional world. So the risk then is, from the look on the process side, you can gain some wafer bowing in your wafer fab. Then okay, it's not so advantageous. Or you have discussed, okay, if you don't want a real copper metallization, you can discuss the so-called DTS. This is the reverse light-up system, basing on this so-called line-force-1 part of DBB. But it's more or less a new metallization you want to apply, because it will sinter a thin copper sheet on the top side, and then it will gain a 50 micrometer layer on the contact of your source, and then you can apply for sure some copper wires then. But it's not so far let me say, the pure world you want to have with ultrasonic wire bonding. But it's possible, okay. Just a short excursus to the substrate. This is an overview, but more than this overview I'm not able to show, because you have the ECPE association will cover such things with a one-day workshop each 4 or 5 years maybe. Please look on the ECPE sites then. This is just to show up the complexity of world just with this very special look on the substrate world. Yes. This says you can discuss this inorganic circuit carriers, so these power substrates, well-established DCB or AMD substrates. In comparison to the power world, you can discuss this as well for the logic world, like thick film ceramics, or the LTCC or the HTCC world. Then you have this world, very special for the second-level packaging, organic circuit carriers, FR4, FR5, PCB, high GG PCB, and such things. As well, you can discuss some flexible systems. You have some hybrids or some exotics in between them. And what is often being neglected, you need a discussion about the integration capability in terms of logic power integration of passive components, the integration possibilities of thermal management. So you have something separated and you have to connect them to each other, the substrate and the cooling system, or maybe there is a chance to integrate them towards one single entity at the end of the day. And with the look of spatial applications, you can discuss something like the enabling for later mechatronic integration with the correct selection of your base substrate. Just one hint regarding a real innovative technology which is already established for the logic world, but it's a little bit hard to implement it in the power world. This is the so-called semiconductor embedding into organic circuit carriers. Just to show a little bit here the process steps, this is the bare die, which is die attached as well on a copper sheet here, but then the copper sheet is the base carrier for the later PCB build-up, shown here on the left column. And at the end of the day, you have something in between the two worlds of first level packaging and second level packaging, because PCB means, first of all, a quite proper and well-established system for circuit carriers of your hardware in second level packaging world, but nevertheless you use it now as first level packaging for the bare die. So it's something in between, and it's quite advantages regarding your demands and requirements for low parasitic, strain reductance parasitic design for wide bandgap power electronics. So it could be a quite intelligent and suitable solution for a lot of wide bandgap related applications then. Just to give you an impression of a real cross-section or of this, the transfer from this sketch to the real world here with this cross-section. Here you see the bare die, here you see the base copper carrier, and then you see this multi-layer build-up, which is quite conventional from other kinds of PCB technology here. Okay, this is a table to differ a little bit and give some hints of differences between the worlds from conventional silicon power modules to wide bandgap power modules like SiC or maybe gallium nitride. I don't want to go in the latest numbers here, maybe I have to update some of them. Quite important, I would say, is the situation that you have to improve your thermal management, because you have a higher, you will receive higher efficiencies in the later systems if you want to apply wide bandgap power silicons. This is one of the main drivers for implementing the latest architectures in SiC or GaN, for sure, but the switches the area of the switches is quite small. The power losses in absolute values are lower, but the switches and the area of them is so much smaller that the power density in terms of power losses is higher. Therefore, you need a higher performance in your thermal management. It's quite important here. Okay, these are some systems aspects. Typically, you use wide bandgap higher switching frequencies in comparison to silicon world. Yeah. Okay, one of the most important requirements and design boundary for wide bandgap power modules is shown here. This here is your loop when you switch in a power module. We have the DC link pins here. This is the DC link capacitor, and this is the lag, the phase lag outcome from this bridge situation. And the voltage overshoot here is directly linked to the gradient. The gradient is from your current. The IBT is more or less given from your application and the design or functionality. If you want then to minimize your voltage overshoot by the switching event, then you have to optimize and minimize your L value. And L is directly related to the geometry, the physics and geometry, mathematics geometry of your power module design. One example which is really smart in solution to minimize this L value is given by example from Semicon company here. So you see the current flow through this half bridge, DC minus, DC plus, to the outcome, to the leg, and then you see, okay, the loop, the area in the loop is so small, and you can receive some, let me say, absolutely no low nanohenries here for your spray inductance. It's quite important for the design of high switching or deep gradient switching wide bandgap power modules. Yeah. So let's switch a little bit more away from the technology aspects to the reliability aspects. I don't want to go into each comment or given statement here in this sketch or this picture here, but the main message here is you have to think from the early beginning about the later application. It's quite senseless to think about, let me say, some certain solutions on a semiconductor level or packaging level if you try to implement in the last 6 months into a start of production of your later application. What this means is you have to think about, you have to think from the system and later application to the front loading in technology in automotive industry. This is the main message from with this slide here. It's quite senseless to select here some technologies without knowledge of the later usage in the application or in the system. We need this so-called front-loading, technology front-loading in selection. We have seen we have this two of possibilities, and you have to know on the later application, even the system level, to go on the early beginning of your technology selection there. Which loads we can expect is very special for automotive applications. Okay, we have these main corners here: electrical loads, thermal loads, mechanical loads, chemical loads. Then we have this cross-interacting situation. Very famous is this mechanical thermal, because this is the stress level for a lot of aging effects in the materials you have applied in your packaging system. Yeah. And from my experience, working now about more than 20 years in this assembly in the connection world, is that we have something like a dualism in this AIT world. Because the loads shown here, okay, a little bit neglecting the chemical side, reflect the function. So we have mechanical, we have thermal, we have electrical. Please remember the slides at the beginning of my presentation. Very important with the look, very special look on temperature, just to highlight this. As well here, we have to consider the person you want to discuss your issue or your task. Because a lot of people, depending on their domain they are working in, they have a certain feeling of temperature or another definition of temperature you want to discuss. Because which temperature in such an ECU, electronic control unit, you can expect? You can expect something like a T-junction. Okay, this is for the semiconductor people quite important, but you can think about the packaging temperature on the top side or something like that. You can discuss the temperature inside the housing of the application. You can discuss the temperature at the interface to the ambient, or is it the ambient situation in the later system. So please keep in mind the definitions of temperatures you want to discuss or you want to define as boundaries, design boundaries or something like that. It must be clear. So consider it as well. The next point, quite important, is the absolute temperature value is not so important. Okay, it is for sure, but please consider temperature over time. Really important is temperature over time, because a lot of material can withstand really high temperatures for a short time. A lot of polymers can withstand for a few seconds, even 250 degrees C, without any, let me say, stronger aging or degradation. But it's a question of loading of 5 or 10 seconds. But if you want to discuss all reliability aspects, you have to discuss temperature over time. Looking on this thermal mechanical situation, two basic loading scenario, and as well derived from that the testing scenario, we have to consider on the one side you have this passive cycling condition. This means more or less the ambient condition, so temperature cycle loading from the outside of your application. So we have an embossment by ambient homogeneously through heating and cooling. We have the possibility for a shock condition in a two-chamber system, or another possibility, you can apply a ramped condition in a single-chamber funeral system then. Typical conditions for applying a test load is given here, -40 up to 125 or even 150. Dwell times around about 30 minutes. It's quite typical, you can apply like this. The second one is this power cycle. It's very important for the power module people because the embossment is derived or generated by current, and you will receive temperature gradients in your build-up. So we can discuss something like a short-term period, then the thermal wave goes just in the nearest ambient of your chip, or you can discuss something like a long-term period for, let me say, loading on your thermal management system or something like that. Two examples come derived from power cycling as pictures from cross-sections, and with respect to the different die attach technology shown in the earlier slides, the upper left picture shows a more or less conventional technology with soldered die attach system, and you can see a highly degraded soldered die attach here. Here at the top side is the bonding situation. It has a little bit of damage, but it's not so heavily damaged like the soldering system. It's a more or less mixed situation. With the change from the solder system to the silver-centered system with high reliability regarding the loads in power cycling, so typically just at one contact show something like a failure mode given here. Yes, and the silver sintering layer is maybe not just at the origin, but it's quite low loaded or low damaged here. So if you discuss a change from the aluminium world in bonding to the copper bonding, which is a casting transform project, this effect maybe is not given any longer because you will raise your reliability with a pure copper system on the top side, and then the question is, which is the winner at the end of the day? Which is more reliable? It is the silver cinder layer? Is it the copper wire? Or have we then, is there then a need to change from silver sintering to copper sintering, and we have then a real highly robust system then? Where does the loading come from? We have the situation of power losses during the switching events in your power electronic systems. This means we have the steady state situation. This is more or less given by the RDS on value of your power semiconductor. But you have this switching event at the beginning and switching on, and at the end the switching off situation. And in loss, the power losses in total is given by all of them as the integral of the curve here during the switching event. And you have to differ between your application, because hard switching events, you have something quite typical for a drive inverter situation here. So voltage and current, they change at the same time, so then this sketch is valid here. And each bundle of switching events will count down your lifetime of your selected technology you have in your power module then. So this is the direct or immediate PCT scenario. But as well, we see soft switching scenario, very special for DC-DC converters or for charging converters. Then the voltage and current phase is phase shifted. Okay, this graph is not so valid any longer, but nevertheless the principle is given. This is quite typical for the converter types, okay, with high frequencies in the switching events, but nevertheless the switching events average to something like an elevated midterm temperature level, and nevertheless then it's more or less related to this TCT scenario. So try to differ. Hard switching means you are in this more or less PCT world. With a soft switching application, you are more or less to this TCT loading scenario then. So, power cycle test. Some information were already given today morning, but I want to add something. The premises for power cycling is given by this sketch, by this cross-section here. The base formula, this is, let me say, the world formula for the power cycling people, because here you see this relationship between the functionality, this is the current, and the reliability, this is the delta T, but they are not directly linked. You need as well the information about the thermal situation, the thermal management, and about your selected die, what about the RDS on value here. So you see these influencing factors, you need information about all of them to derive a proper situation for the power cycling test again. This is a typical lifetime curve, the blue one. You see maybe for a certain lifetime data point, you see then degradation in the as a bond wire lifter, for example, or degradation in your die attach here. And then you can change this technology, the base technology, as shown by the slides for the sintering or something like that, or the change from aluminum bonding to copper bonding. Then you will shift your lifetime curve to higher values here, but it's had twofold benefits. Benefit number one is looking on the vertical way ahead. You then have a higher robust system by this implemented new technologies. This means of the same delta T stress level, you will reach higher numbers of reliability or functionality then. The benefit number two could be more functionality, because you can say, okay, the number of lifetime is given, I don't need more, but then you can raise your stress level to higher delta T values. Additionally, in this graph, put it as well, but it's not so correct, because if you want to discuss TCT, you need a separate lifetime diagram then, but just for showing the principle, the same discussion you have to perform with TCT situation here, and then you have to a certain look on the substrate to base state situation. So the connection to the thermal management is highly interested under TCT loading, and then in principle you need the same diagrams and the same curves here. Okay, this was the second main part. Coming to the third part, standardization. Some information were as well given today morning from early presenters. I want to cover 4 points. Automotive Electronic Council, oh sorry, this is a break, my hands should be broken down here. Then robustness validation, then to AQG and JD. I would say these 4 are the most important ones. Okay, AEC. This is one of the most important things you have to consider in automotive electronics, because it's well established. These documents you can you can receive it by free download, I would say, from the AEC, from the AEC internet links. Okay, they are absolute dominating the automotive industry. They are so highly well established. But you have to think about this first point given here. Originally, they are developed just to let me say, to assure quality for shipping first testing samples to the customer. This was the origin of these documents, but now we use them for the qualification process of the SOP of the later product. It's a quite interesting development if you see the history of such qualification documents. So meanwhile, the Q standards of AC act as the worldwide accepted automotive reliability base for the usage of discrete active devices. Well, the Q200 series as well addresses the passive ones, the passive components ones, but we are discussing now the active ones under later field loads. It's quite interesting that we want to cover this. For instance, some tests here excerpt from these documents. I don't want to go into too much detail here. Just as a hint, this is more or less the origin base for automotive reliability. If you try to compare some details to power modules, you can look on OK. The semiconductor packages addresses discrete for logic or ASICs, discrete for power. Okay, bare die is quite typical for power modules. There's multi-chip power module. We have bare dies in that. The qualification referred to AC Q100 considers predefined stress tests with predefined load conditions. And this is the statistical base, quite interesting. Regarding this shipping situation at absolute origin, 3 lots maximum with 77 pieces. So the statistical base is 231 devices, which is covering just 1% failures at 90% confidence level. It's quite interesting. This is the assurance level which we now address, but a lot of people talk about ppm, parts per million, or ppb, yes? So it's quite interesting, different a lot here between the let me say, the level or you want to consider. We have just passed, not passed criteria, and okay, objective in its origin, approval of samples for customer operation. Okay, but just discrete world, not the power module world. What critics are raised in the last 20 years regarding the AC unit? The consequences given from this document landscape is we have a common qualification procedure that relies on predefined stresses with predefined stress conditions. These stress conditions do not bear no relation to the later application conditions, and the test is passed if no failures are observed. You can say, 231 pieces, I have seen no failures, I'm happy. This is the problem. I feel good, I've seen no failures. In this context, there's the psychology of ignorance. You know about your project, there's a need about knowledge of your reliability, and then you have to see failures. This is the base problem. If you want and have a good feeling about the design, the implemented front-loaded technology, you have to test until you see failures. This is the base problem here. And therefore, there was a change in mindset, there was a change in methodology, a little bit away from this AEC world, because we need something like robustness validation. This means you know about the borders, the robustness margin to the real end-of-life situation under certain stress conditions. This methodology base changed from the early beginning on the semiconductor level, but is nowadays available for ECUs and sensors as well. I don't want to go into too much detail here, but just a hint. Let's go to the ZEI Association, and the homepage is there. You can download as for free the documents here for all of these components, and quite important for sure is the semiconductor one. Regarding this change in mindsetting from AEC to this robustness validation methodology, the AQG world was generated, or arose from another horizon. Because we have seen AEC does not cover the multi-chip power modules. We need information about robustness in terms of lifetime data, tested until end of life. And there was no common bracket about all needed test procedures to qualify properly an automotive power module, very special for the drive inverter. Therefore, an initiative was started around about 12 or even 13 years ago from the so-called supplier management from the German VA Association. But nowadays we are now arranging it as the ACPE guideline AQG 324. Okay, you see a short overview on the testing scenario. Tobias showed it as well today in the morning. Most important I want to highlight is the green one. Because this is really determined by the mindsetting of this robustness validation. The power cycling routines on the short time scale and the long time scale, they are defined. You have to test it until the end. You have to see the failures. You need a lifetime curve under this power cycling condition. Let's have a short look on JC70. Okay, this committee is driven really by the semiconductor industry. The AQG world is driven by the power module people, because here we want to qualify the power module. Ideally, we don't want to look too much into the needs or the characteristics of the power semiconductor which is implemented in the power module. But it's quite, yes, it's not. We cannot perform without knowledge of the power semiconductor. So There's a little bit of, let me say, grayscaled interacting between the power module qualification and the power switch power semiconductor qualification, which is covered here by the JC70, because the JC70 people, they cover wide bandgap power semiconductors. The dot 1 is the subcommittee for gallium nitride, the dot 2 is the subcommittee for SiC. Okay, they want to talk about reliability verification and qualification procedures. Okay, it's nearly the same. We want to do and perform with the AQG 3 to 4 for the power module level. Test methods and measurement techniques, datasheet elements and device specifications. They want to cover unique packaging considerations, cataloging and consideration of mission profiles. Okay, here's as well the lifetime aspect involved. Formulation of terms, definitions and symbols. We have between AQG and the JD people, there's a cooperation base. So we try to interact intensively, but it's nevertheless quite hard to get information quite early from them to consider it for usage in the AQG for the power module world. Okay, my summary to take away. First of all, we have a globalized supply chain and value creation in electronics industry, and this is started as well for power electronics world. I try to show you that power electronics is a quite cross-disciplinary work in terms of science of materials, physics, chemistry, electronics engineering, mechanical engineering. So you need knowledge about all of them. Even you will not be successful with your design or your later power electronics prototype. Where with this very special look for wide bandgap power semiconductors, let's say, okay, on the one hand we need low inductive design, so this differs a little bit to the silicon world. So we have maybe you need something like a change in mindsetting about the circuitry you want to design. This means in terms of the load circuitry and as well the control circuitry for the power module. You need new technology variations or even completely new technologies beyond state of the art. Very special with the look of reliability demands. High temperature capability due to higher an application usability junction. This is the situation in this power cycle lifetime curve. No? You have more functionality, more lifetime. What do you want to get out of your application? And you need thermal cycle robustness in TCT and BCT. This is very important to the automotive people. This is not so the case for the industrial world. If you just try to implement your power electronics application in let me say a fabrication or manufacturing side or something like that. For a mobile car in a certain global ambient, maybe in Asia, Europe, North America, South America, you need knowledge about the loadability of your power electronics. Qualification routines, general ones, or even new upcoming specific ones, they will support this industrialization of new technologies, even on the first step, on the semiconductor level, on the second step for the power module level. And never forget, wide bandgap power semiconductors are quite precious devices. So all your demands, all your selections activities, all your design activities regarding AIT, you have the selection has to support the outperformance of these wide bandgap devices. So this is my last message here, because a lot of you are it could be that a lot of you are quite highly involved in, let me say, circuitry design and theoretical considerations of your late application and so on. But at the end of the day, you will sell a physical incarnated product and not a circuitry design to your customer. So the transfer from, let me say, simulated virtual world of power applications to the later product needs this physical incarnation. Assembly and interconnection technology has to be mastered. I try to show up this intensively in my second part, and wide bandgap power electronics demands new design problems. Okay, thanks a lot.